Good morning. It's time to talk about our next topic. We're going to discuss the death of the star. Oh, oh, you will not survive. Yeah. Okay, so when we discuss the death of the stars, what we're talking about is basically we start when we talk about the main life of the star. The main life of the star is the time it spends on the main sequence, and that time is actually determined by the mass of the star. The larger the star, the more massive the star is. Then what happens is that it burns its fuel that much more quickly. So the high mass stars are very bright, they burn quickly, they run out of fuel, and they blow up. When the medium mass stars sort of goes through their fuel, but takes a lot longer. They kind of become a giant. They don't blow themselves up though. And then the low mass stars just kind of hang around for even longer than the universe is old. So that's this kind of first part here. And there's a diagram up here, but I'll actually get into that diagram a little bit later. Let me go ahead and stop the share here. So we're going to talk about the deaths of stars here. And chapter 10, I'm going to separate into two parts here. So the first one, we're going to talk about the deaths of the stars. What happens to the stars after they run out of their fuel? So the stars have hydrogen, and in their cores, they're all converting hydrogen into helium, just like our sun is. So our sun is converting hydrogen into helium in its core. What happens when that runs out? And the type of death you end up getting just depends on the mass of the star. So gas clouds collapse. If there's sufficient matter and pressure, core sustains nuclear fusion, and it comes on. You get the total reaction, kind of looks like this. You have 4 hydrogen nuclei going in. You get a helium nucleus plus some byproducts, and you get energy out of it. But of course, we want to know what happens when it runs out. So all the main sequence stars have the one thing in common is they produce their energy by fusing hydrogen into helium. And so we want to ask the question, what happens when a star runs out of its hydrogen? And the fate of the star, once again, it depends on the star's mass. And the main sequence stars are all in what we call a state of hydrostatic equilibrium. It's where the pressure from the gases underneath is just enough to hold up the weight of the star. So there's 2 forces enacting on a star at any time. It's the gravitation that wants the star to collapse, because remember, this is gas. Gases are collapsible. And then there's the gas pressure that is trying to get it to expand. So with the low mass stars, they're less than 40% the mass of the sun. So in other words, when we're talking about all of these star masses, we're always comparing them to the mass of our sun. It's just the easiest thing to do. So anything less than about 40% will have convection throughout. They'll never become giants, and they're not even old enough. The universe isn't old enough to run out to have any of these run out. Their lifetime, so to speak, on the main sequence, it measured in the trillions of years. I mean, this is the thing. When you talk about these big, lifetimes of stars, there's a huge variance. The stars like these low, what we call them as red dwarfs. They're red main sequence stars. They're not like white dwarf. White dwarf is something completely different. But there's red main sequence stars, a big bunch of little red ones at the bottom of the HR diagram. And that's why. And they'll last trillions of years. The universe isn't even trillions of years old. Best estimates put it in the billions of years. So not trillions of years, billions of years. Yeah, well, that's boring. Okay. So the medium mass stars are anything between 40% and 4 times. This includes our sun. Our sun is a medium mass star. And since we're kind of solar biased, it's I'd like you to try to remember what happens to our sun. So our sun's inner layers are, oh, I got my email opened up and it went boing at me. Hang on. Don't need to go boing at me anymore. There we go. All right. So the thing is that the sun has three layers. It's got a core, it's got the radiation zone, and it's got the convection zone. This is the interior. Outside, of course, then you have the photosphere, the chromosphere, and the corona. Those are the outer layers. Those are the atmosphere. So the core is the only region that is hot enough to produce for nuclear fusion to act. It's the only region hot enough. The rest of it isn't. The core isn't stirred convectively. Convection isn't the main source of heat transfer. The main source down around here after you get out of the core is radiation. So there's nothing really stirring that helium up. So when you convert the hydrogen to helium, that helium just sits there and does nothing. Helium sits there, does nothing, because the sun is not hot enough in its core to fuse helium. So it'll just sit there and build up, okay? So it has more mass, so it kind of sinks more to bottom. And you kind of get this little onion effect where you got an outside. So here, the sun has used up almost all of its hydrogen. This is the helium, and the blue area here is our helium. So that's helium-dominated region because the helium is going to sink. It's heavier than the hydrogen. And then you've only got this little tiny ring shell of fusion here. So what happens is that, oh, well, there's not enough energy being produced in there to hold up the weight of the sun anymore. So the sun is going to collapse. So what happens is the core does two things. The core collapses under gravity, but also that collapse causes it to heat up. So if we look at it from the outside, from the shell, what we see now this heats up. This is going to heat up more. It's going to cause more of this hydrogen to be available for fusion. So what the shell is going to see is, well, there's not less energy. There's actually more coming up from that core. There's actually more than before. So what the shell ends up doing, so this nice little yellow shell that we have now, is going to start expanding and cooling off. And the sun will bloat up to become a red giant. So this is the sun as a red giant star. Now, at its maximum red giantness, the sun will envelop the planets Mercury and Venus, and probably the Earth. So we'll be inside the sun. If we are not inside the sun, we will be so close to being inside the sun, we might as well be. You know, trying to live on Mercury today, you know, it's just not going to happen. Now, at some point during the red giant phase, the sun will obtain temperatures hot enough to fuse that helium. And so it can go one more step further. And this actually is said to begin suddenly. It's not an explosion, but it does suddenly start converting the helium into carbon. So helium gets converted to carbon, and that's called a helium flash. And then that will say, okay, well, that now fuels the sun for a little longer. And then eventually it can't really do it anymore. So what happens is that the sun begins to pulsate like this, and it starts losing its outer shells. Its outer shells start getting ejected in space like waves. Waves come and push the outer envelopes outside. And so you get this waves of gas surrounding. So basically the core is basically ejecting all the rest of the shell. So what you end up with is a planetary nebula surrounding the core, and the core shrinks so much because the gas can't hold it up anymore. So it actually shrinks down, and it creates this weird state of matter where overcrowded electrons, referred to as degenerate electrons here, will hold up the weight of the star. And this whole idea of electrons being degenerate and being able to hold up the pressures of lots of matter. That actually comes from quantum mechanics. If it were for quantum mechanics, there would be nothing to hold up the weight of the star and just collapse. Nothing. So the sun's core will become what we call a white dwarf. Talk about that in a bit. There's no more fusion happening in the white dwarf. It's just carbon and oxygen, mostly carbon with a little bit of oxygen, because sometimes, if you get 3 of these coming together, you get carbon. If you happen to have a 4th along for the ride, then you'll get oxygen out of it. Okay. And the core, the white dwarf thing will be about the size of the Earth, and it'll be about 40 to 60% the mass of the sun. So those are the things that are going to happen to our sun. Now, the sun is currently estimated to be about 5 billion years old, estimated about another 5 billion years left on the main sequence, but it will be getting hotter, like 10% hotter every billion years, even before it runs out. So hopefully within a billion years, we can either escape the planet, go somewhere else or something. I don't know. I won't be around. So that's a medium mass star. Now let's take a look at the largest suns, the large mass stars. Okay. These are any stars with a mass that start out with a mass 8 times the mass of the sun or bigger. And a lot of mass can be lost during a lifetime. What happens is we talk about what we call heavy metal fusion. Now, in astronomy, a metal is anything except for hydrogen and helium. So it's just hydrogen, helium, metals. So in other words, in astronomy, we don't distinguish between all the different elements. If it's bigger than hydrogen and helium, it's metal. Especially when you start talking about stars and stuff, because your fuel is mainly hydrogen. If the star's hot enough, then its core can use helium. And if it's even hotter, then it could do this, what we call heavy metal fusion. So there's a few tricky things about this. So let me put up a, let me grab your text. Let me find a place where it is. Okay. Let me share this first. Okay, so let me zoom into this picture here. There it is. And this is still the core of this gigantic star here. So the rest of the star is actually outside of it. With all the rest of the star would have non-burning hydrogen at this point. So each time it does a nuclear fusion, it gains some energy. So in other words, some energy is lost out of the nucleus, and we get that energy. So we can gain energy from going from hydrogen to helium, from helium to carbon, carbon to oxygen, oxygen, neon, magnesium, silicon, iron. The problem when we get to iron. And I'm going to show you a chart, even though I don't want to explain it to you too much. I just want to show you some implications of it. G per nucleon. There we go. Don't you give me a, I hate you, AI crap. I hate Google. I hate Google's AI stuff. Come on. Come on, I clicked on the right picture. This should be it. There we go. Okay, there it is. Aha, now I can show you this. Here we go. All right, so this is what we call the nuclear binding energy per, the binding energy per nucleon. And basically this shows you how much energy you can get when you go fusing things. Notice that when you go from hydrogen to helium, you get a huge amount of energy out of that reaction. Huge amount. And by the way, the amount of energy you gain out of those nuclear reactions is equivalent to the amount of mass lost. So in other words, you can calculate it. So way back when, if you remember in school, you had the conservation of energy. Energy can't be created or destroyed. It can only change form. Remember that? Ain't that exciting? And then there was another one, conservation of matter. Matter cannot be created or destroyed. It can only change form. Well, not exactly. In this nuclear fusion case, if I take the 4 hydrogens, the 4 hydrogen nuclei, they weigh more than the helium nucleus you get, plus all those byproducts, all the rest of the mini byproducts that you get out of it. In other words, there is an overall mass loss. An overall mass loss. So mass is lost. Uh-oh. Well, wait a minute. You're gaining energy out of this process and you're losing mass. That seems to violate both of those things, right? It violates the conservation of energy and it violates the conservation of matter. Except somebody showed us that, wait a minute, mass is energy. And you can even calculate how much energy you get out of losing so much mass. Okay? The formula looks like this. E for energy equals mass m multiplied by what? What will I multiply? So I'll put a blank over here in this little equation I'm typing for you. E equals m, and what do I multiply by? E equals m. You've heard of a formula E equals m something, right? And yes, it's that formula. Come on. You can unmute and tell me. Or type in chat. Just type in chat. What I should put there. There you go. You guys are too shy to talk. But yes, putting in chat. Yep, that's it. E equals mc squared. So that calculates how much energy you get when you lose mass. Okay? Now the other thing is that in big, larger explosions, and in fact, when they talk about certain collisions between strange objects and stuff like that, that's where the really heavier elements get produced here. And these elements gain energy not by fusion, not by coming together, but by breaking apart. And so when we talk about nuclear energy here on Earth, we're talking about nuclear fission. We take our uranium and we have a controlled reaction of uranium. Has to be controlled. And that's how you produce energy. What do you think we would produce if we didn't control the reaction? We wouldn't produce energy, we'd produce something else. If we don't control the uranium reaction, what happens? Nuclear reaction, if we don't control it. Here, I'll give you a hint. Anybody watch Oppenheimer? Yeah, that's what basically did. You get an explosion. If the reaction isn't controlled, you get an explosion. So the trick with Oppenheimer is the Oppenheimer thing. He had this design where he had this shell of stuff that would cause an initial explosion, push all the things together. So it actually ended up fusing some things too. And then it just exploded. And that's just energy, except it just isn't controlled. If you don't control it, it just goes wherever. The A-bomb there. That's why on our power plants, they have to be safe. They have to, nuclear power plants, you have to be really safe. And that's why any power plant should have several nuclear power plants. They have several safety mechanisms in line to shut it down. It takes a while. Yes, it would take a while to bring it back up again if you shut it down, but that's better than having something explode. The last time we had a nuclear accident, I think, was after that tsunami. It hit Japan. That was scary too, because that's what happened. Is basically, I mean, I guess they don't build nuclear power plants thinking, oh, a tsunami is going to come in and basically mess up everything. So thank goodness. So there was like radiation leaking out of that plant until they finally got in there and was able to shut it down. And then the other the big famous nuclear meltdown was Chernobyl, and that was because of the I don't want to speculate because it's something to do with the culture and the government over there. So in the 80s, when everything was hush hush and you don't dare criticize anybody, and you don't dare say this isn't working, you don't dare say it. So people just didn't say it. It's just, oh. Anyway. Now, so if you're over here, you want to fuse, you want to break apart. If you're over here, if you're over here, you want to fuse, put together. If you're over here, you want to fizz, break apart. But the most stable nuclei are right here. And when you get to this iron 56, that's the most stable nucleus. If you try to fuse iron, it won't give you energy. It'll actually take away energy if you try to fuse anything into iron. And by the way, if you try to break apart iron, it will also take energy from you. So once you get iron, you can't get energy anymore. Once you get iron, you cannot get energy. There's no more nuclear energy in there. It's all done. So what ends up happening is, we'll go back over here. PowerPoint. No, I need to go back to this point right here. What happens is this iron can't fuse to do anything. So it just builds up in the core. In a heavy star, this builds up in a core. Now, the thing is that those degenerate electrons are pretty good at holding up weight in stars, but they can't hold up everything. Once this passes a certain point, the iron core here, this big giant iron thing, with a bunch of iron nuclei in it, once it passes a certain point, the electron degeneracy is overcome. And that whole iron core just collapses in an instant. It collapses in on itself. In fact, it collapses until nuclear forces would take over. Remember this talk about the size of the atoms, though. An atom is 100,000 times larger than the nucleus. So what happens is, all of a sudden, this thing shrinks. This would be about the size of the Earth here, held up by those degenerate electrons. Shrinks to about the size of a city. And during that time, it releases a huge amount of these things called neutrinos. That's one of those byproducts. And normally the byproducts just go through the star. But there's so many of them. And they're all coming out at once, because this thing just, basically, you just take an entire star that's sitting up here on top of a thing, if you measure it, and you just ripped out the bottom. You just rip it out. So what's going to happen here is this is going to fall in on itself. Well, you can't fall in without having a rebound. So what happens is it falls in, rebounds, and the whole star just explodes. Okay? And explodes in what we call a supernova. Here it is. No, see, there's an iron core. And then the star just explodes. Explode the star. So this is what we refer to as a core collapse supernova, otherwise known, oddly enough, as type 2. Yes, there's another way to make things go supernova. Cool, huh? There's more than one way to destroy a star. The Sith put the iron in the star of Tatooine, and now it's going to explode. Rey won't be able to fight me anymore. I came back for the dead once. I'll come back again. Because it's Disney and they need a villain. I mean, they killed off that Snoke guy in the second one. I don't know too much. I actually didn't watch the second and third one of the new trilogy, but I just heard about it. I'm like, oh my God, what did they do? Anyway, there it is. All right, so what happens here is that the core collapses and you get a supernova explosion. So once you get to the iron, now it depends on what's left in the core. So the whole entire star explodes and it creates what we call a supernova remnant. So I'm going to show you the difference between a planetary nebula, like things that'll be made out of from our sun, and a supernova remnant, which is made from a supernova explosion. Okay, so let's do this. So let me just share the screen here. Okay, so let's share this planetary nebula first. So see, look how nice and orderly this is. There's a nice little pattern to it. This is because these planetary nebulas are created over millions of years as the star is slowly shrinking down. And so it's a very orderly process of the star slowly dying. You can think of it you can think of that like a death shroud around the, around this thing in the middle, which in this case is going to be a white dwarf. Our sun will eventually become a white dwarf. See, they're pretty. Look at these things; they're pretty. Okay. Now I'm gonna pull up the supernova remnant. Okay, show you what it looks like. There. It's a jarbled mess. It's a mess because instead of being made over millions of years, it's made in like fractions of a second, and then it just expands outward after that. See, there's just no real order to this. It's all over everywhere. It's just like you spilled something, You didn't take your time doing anything. Just blew off into space. Okay? So that's the difference between those two. Now, what's left in the middle? Well, what's left in the middle depends on what the mass of the core that's left. The mass of the core that's left in the center. That's what's going to depend. If it's a low enough mass, then what can happen are the neutrons can take over where the electrons couldn't. And the neutrons hold up the weight of the star, just like the electrons would. They're called degenerate neutrons. They're degenerate neutrons, and they'll hold up the weight of the star. But if the star is even heavier than that, then we don't know any force that could hold it up. Not before it shrank down to the point where no light gets out of it. And that creates one of the weirdest things is a black hole. Let me go back over here. So now I'm going to share this the time figure here, because it all depends on how much mass the star has. And they don't even include the very lowest mass stars because they're just still going on trillions of years. The heaviest stars, the ones that blow themselves up in supernova, their lifetimes are measured in the millions of years. Lifetimes of our sun measured in the billions of years. Lifetimes of the little red guys, trillions of years. That's a huge difference. Astronomical scales. Our sun lives 1,000 times longer than the biggest stars. And the little stars will live 1,000 times longer than our sun. Is that a trip? It's just how much that spread is. that spread so much. We have about millions of years, billions of years, trillions of years. So when a stellar makes an average star, like our sun, it becomes a red giant eventually once it leaves the main sequence. As it shrinks down, it will make the waves and make a pretty planetary nebula. And in the middle of it's the thing we call a white dwarf. More massive stars, they get to have fun. They become supergiants, and then, of course, become with the iron, and the iron shrinks and it blows up in a supernova. And then after the supernova, we either get one of two things. We get a neutron star or a black hole. So this is where I'm separating it to the second part of the chapter here. Just the second topic. In your chapter itself, these are all kind of intermingled. I like to separate them because they're kind of talking about, two different ones, talking about things blowing up. And this part's talking about what's left behind. It is time to mourn our dear lost stars. Okay. So there are three things what we talk about when I talk about stellar corpses. The three things that are left over. There's the white dwarfs, there's neutron stars, and there's black holes. And these things are called compact objects. They're not even solid objects. In other words, they're not held up by atomic pressures. They're held up by degenerate electrons or degenerate neutrons, or not held up by anything, not held up at all. So let's take a look at the white dwarfs first. So the white dwarfs have a mass of the sun. It's shrunk to the size of the Earth. It's held up by what we call degenerate electron pressures. And inside of there's carbon, mostly carbon, and a little bit of oxygen. So here's a sort of question. We ask ourselves the question, what if mass is added to it? What if somebody were to scoop mass and put it into the white dwarf? What happens is that the white dwarf will actually shrink because those electron pressures kind of stay the same. Gravity increases a little bit, so it'll shrink to find a new equilibrium. Well, you can't shrink to nothing. And so if you add too much mass to the white dwarf, you'll get a point where it just can't exist anymore. So eventually, if you add mass to that, the radius will shrink to zero and you can't do it. So the way that the white dwarfs have mass added to them is if they're in a binary star system. Because in a binary star system, you've got another star nearby that will blow up into a red giant. And if the gases get close enough, the white dwarf could siphon them off. Any of these compact objects could siphon off mass from giant stars, any of them. There's a particular limit that they calculate, Chandrasekhar limit, and it's 1.4 times the mass of the sun. And so that is the maximum mass that a white dwarf can have. Now, what happens is if the mass exceeds that, then a white dwarf collapses. If the whole thing collapses, so if all of it collapses, sometimes it's just a shell that collapses. That's a little different. It's what we call a nova, but not super. But if a whole thing collapses, then what happens is that when it collapses, unlike the iron core, the core of the white dwarf can react. The iron in the whole thing cannot react. Iron can't do anything. So it has to go down and become the neutron star. but this one will react. So all these things react, and it just blows up the whole star. So the whole star blows up, and there's nothing left, where the whole white dwarf just blows up. And this is what we call a type 1 supernova. This is a type 1 supernova, adding mass to a white dwarf and making it blow up. The cool thing about it is it always blows up with the same mass. If we see a white dwarf blow up, then we know, oh, it had 1.4 times the mass of the sun. So we can study those because we know exactly what's going to happen. We know exactly how bright it should be. We know how it is. We know all this fun stuff about it. Cool, huh? See, if we know how bright something should be, then we can tell how far away it is. We can see how bright we see it and say, it's type 1. There we go. Type 2 is a little difficult because type 2, the problem is that we don't know the mass of the star to begin with. So like a type 2 with a 20 mass solar mass star would be brighter than a type 2 with a 10 solar mass star. You see what I mean? That one I can't tell. But this one you know because every time it does it, it's done at that Chandrasekhar limit. Okay. So those things. All right, so then you have the neutron stars. Neutron stars, as a mass of the sun, it's shrunk to the size of a city. It's held up by degenerate neutron pressures. It's basically a big ball of neutrons. It's a big ball of neutrons. These neutron stars have huge magnetic fields because all the neutrons have magnetic fields. And when they get together, they do kind of like to line up with each other. So basically you get a giant ball of neutrons all lined up with a magnetic field. And so we have the short, precisely timed radio bursts, and those ones are called pulsars. And we have a prevailing theory about that is to have it what we refer to as the lighthouse theory, because we think of the neutron star spinning like a lighthouse. And whenever the beam passes in the direction of the Earth, that's when we notice the pulse. Boop, boop. We notice the pulse from this. Here's the pulse. Pulse, 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 pulse. Regular pulses. Now, the other thing, these pulses are very fast. Remember, the sun is we did it when you looked up at stuff in chapter. It's the rotation of its equator is 25 days, 25 Earth days. This is moving around every, second and a half or something? And it's even more massive than the sun. It's really fast. So how does it do that? Well, I have to make a silly demonstration. So if you ever watch the Olympics, anybody watch the Olympics? Come on, say yes in chat if you ever do. Because I've got to talk about an Olympic sport. And unfortunately, the Olympics aren't as big of a thing now as they were back in the 80s when we had the Russians and we wanted to do better than the Russians. And now, there is a sport. It is a judged sport, so it's kind of really quick. The people do have to be athletic doing it, but they also have to kind of look pretty or look fancy or do other things like that. And it's a winter sport. And so, anybody guess which sport I'm talking about? They have to be athletic and jump and spin and turn around, but they also have to look good doing it. Almost ice skating, almost, but what skating do you have to look good when you do it? It's not just that you can do it, you have to look good doing it. Because if you don't, there you go. Figure skating, there it is, yes. So in figure skating, you don't have to only do the jumps and stuff, you have to be good doing it. Oh, you didn't smile at -5 points. That's the only problem. There's all kinds of collusion or whatever it is. Anyway, when the figure skater goes into that spins like this. They start out with their arms wide like this, and then they pull their arms in closer. And then what happens when they pull their arms in closer? Anybody remember? Skater, what happens when they pull their arms in? So they start a spin, they have their arms out wide, they pull their arms in. What happens? What happens is that they spin faster. And that's what they do. That's the conservation of angular momentum. So in other words, they don't have to do anything. They'll just pull their arms in, they'll spin faster. They don't have to try to speed up the spin. They just start it with the spin, pull their arms in, they're going to spin faster. And they spin really fast, and they have to stop like this and smile. So that's what we call the conservation of angular momentum. And if you imagine how much that star is pulling in, basically it's taking something that's at least 1.5 times the mass of the sun, probably 2 or 3, and suddenly taking it from the size of the Earth down to the size of the city, 100,000 times smaller. You have to, I think you have to square it, something like that. And so it has to spin like 100,000 times more to get someone like 1 billion times faster than it was before. So yeah, those neutron stars are spinning really, really fast. And if we happen to be in the area where the thing is, that's when we'll see the pulses. So those are our pulses that we see. And those are pulsars. Okay. All right, now, we'll talk about two things here. All right, so black holes, we don't know what happens inside a black hole. The matter theoretically is shrunk down to a single point, which we call the singularity. We call it a singularity because it's a mathematical place where the formula just breaks down. Basically, you're dividing by 0 squared. You divide by 0 squared, it's going to be like infinity squared. No, that's not getting good. That's what happens. Oops. So the only thing that we actually observe is what happens kind of outside or on the boundary. If we think about our escape velocity, if we move a body fast enough on any surface of any body, if we move that body fast enough, then we can escape its particular gravity. If I have something on Earth's surface that's moving at 11.2 kilometers per second, it will move fast enough. It will go out into space and escape Earth's gravity. So on Earth's surface, that's the speed you would need. You need a bit more on the sun. You need 615 kilometers per second to escape it. If you're on the surface of the sun and you don't burn, and you have that speed, you'll escape. Now, the heavier the object and the smaller the object, the more the escape velocity is. The more massive ones, it's obvious because you got more gravity. But the smaller the object is, that means you're actually closer to the center of that gravity. So when you start talking these compact objects, those escape velocity gets huge because you're now closer to it. So down a white dwarf, it's over 6,000 kilometers per second. And then a neutron star is 150,000 kilometers per second. Basically half the speed of light. If the thing is collapsed so much that the escape velocity is greater than the speed of light, well, the speed of light is the fastest speed that anything can go. And that's a relativity effect. So if this class were more advanced, you'd have to do all kinds of fun. Here we just go over the concepts enough so you understand how relativity works in terms of these stars. Nothing can go faster than light. So if the escape velocity is greater than that, well, you can't escape it. If nothing can escape it, not even light, it's a black hole. We can determine the size of a black hole, but it's not really a size. It's just where the boundary would be, that nothing closer to that would escape. And when Einstein made his general theory of relativity, he didn't. It's an equation. It looks simple because it's just one line, but it's like 10 variables in that whole. They compact everything. It's actually 10 equations of this and that and the curvature and blah blah blah. And somebody found a solution. Yay! Schwarzschild. And now his Schwarzschild is, the radius, the Schwarzschild radius, which is how far you can be away from a black hole before you fall in, where the boundary is. And you just put in these constants, and where m is the mass of the star. And then I kind of transferred it over here to give you an approximate thing. It's an approximate thing. So if you took the mass of the sun and shrunk it down to 3 kilometer radius, it would become a black hole. Well, the sun's going to become a white dwarf. It's not going to get anywhere near there. A neutron star has a radius of about 10 kilometers, and its Schwarzschild radius would be about 6 kilometers. So we're getting closer, but we're still not there. We're, because 10 is bigger than 6. I have to shrink it down smaller than that. Okay. So, but if you keep putting mass in there, eventually the mass of the Schwarzschild radius will move outside of whatever it is you have, and then that air region is just going to become a black hole. So a black hole has, like, basically singularity is where you think a point all goes to the middle of it. Point goes to the middle of the black hole, where all the matter is said to be concentrated. Basically, we're not sure, we don't know, but when we take into account black holes, when we do any kind of real calculation in the real world, we can only test the effects outside of the black hole. And the boundary of black hole is called the event horizon. In other words, anything that happens outside of a black hole would be able to be observed by distant viewers. So in other words, we're over here. We're always distant viewers from black holes. We don't want to be near black holes. Okay? So outside of black hole, anything that would happen or occur inside the black hole, we would never observe. We have no idea what's going on outside the black hole. Outside, by definition. I mean, even if you went inside a black hole and you found a giant poodle inside of a black hole, you would never be able to come out of the black hole to tell everybody, hey, there's a giant poodle inside the black hole. Now, how do we find black holes? Well, we don't find black holes by looking at observing the black hole, because you can't observe a black hole. It's black. There's nothing coming out of it. What you can is observe the space around it. So what happens is we'll find these air regions of very large X-ray sources, but you look and there's like nothing there. There's no visible, nothing else there in the middle. There's like X-ray sources coming from nothing. Well, the X-ray sources happen because when matter gets pulled into a black hole, the electrons in the matter start accelerating a lot, and they start hugely radiating out stuff in X-rays as they heat up. And so what you can think of is those X-rays that we detect are like the last screams of the electrons as they get pulled into the black hole. Ah! Like that. And once they go inside, that's it. So what would happen if you jumped into a black hole? Yes. Let's take a trip into a black hole. All right. There's a couple things about a black hole. First of all, on Earth, let me do this. Okay, so on Earth, your feet are just a little bit closer to the center of the Earth than your head is. Your feet are a little bit closer to the center of the Earth than your head is. Well, the atomic bonds in your body easily overcome that little bit of difference. It's basically a tidal force. But near a black hole, the tidal forces are huge. So what happens is your body would actually get stretched as you fall into a black hole. So that's one of the things that would happen. So basically you would end up looking like this. And you stretch and squeeze like this. And you fall towards a black hole. It's not like this. Whee! Want to get skinny? Just go to a black hole and jump in. Oh, you get skinny. And basically, the tidal forces of the black hole will tear you into your constituent atoms. And that's what we call spaghettification. Basically, it pulls you out like spaghetti. I know that's a silly word, but that's what we call it, spaghettification. Okay? So let's assume that you could somehow survive that. Okay? A couple of other relativistic effects happen as you move near the black hole. First of all, as viewed from outside, your time slows down. In the gravitational field, time slows. So there's time dilation going on. The other thing that happens is that the light from your body is actually redshifted. Any light is redshifted as it escapes that gravitational field. So eventually at the boundary, no light could get out. All light that's emitted close to that boundary is going to be what we call redshifted. So it's going to turn red. So let's see, I'm going to jump into a black hole and I'm going to put the event horizon here. So that's the event horizon. Singularity is back there. Okay. So I'm going to jump into the black hole. Okay. Now, as I get closer and closer to the event horizon, millions of years from now, people will be looking up and say, there's that stupid professor that jumped into the black hole. Basically, at the event horizon, as observed from outside, time stops. Meanwhile, from my perspective, I'm already chilling out at the singularity. If all in, everything's normal, I go to singularity at the end. As observed from outside, time slows down, becomes redder, and eventually it's kind of frozen at the event horizon. Really strange thing. And so here's my little things. So falling into a black hole. These are the three things. Gravitational redshift, so light escaping around the black hole. Wavelengths are stretched. Time dilation near a black hole. Moves slower when viewed from outside. And then spaghettification. If you have a larger black hole, you can actually survive the spaghettification part for a large black hole. You'd still get spaghettified, but it would be inside the event horizon. Nobody would see you get spaghettified, but it doesn't matter because, you know, set this thing up. Mm, mm. Let's see this. All right, so if you refresh your Canvas pages for the ones in my regular old section, refresh your Canvas pages and then go down to the CPs. We're on N20 and the access code is Supernova. For our guests, you don't have this. Our guests from the later section, don't worry about it. That is not for you. That's for the people that are in the class that meets. And the access code is Supernova. Woo! All one word, Supernova. And I will type this word in chat. Supernova. It's all lowercase too. All lowercase. All lowercase. That's all lowercase. All right. That's it. Work on assignment 10, and it's due next Tuesday. We will not be meeting next Wednesday, so you guys also have a nice Thanksgiving. Okay. We'll meet you the week after to wrap things up. All right. Have a nice day. Have a nice holiday. I might see some of you before then, but no. Have a nice Thanksgiving. Oh, I better stop the recording.